All right, time to head from the sublime to the ridiculous. Time to take a look at some hyperbolic geometry and how area and defect play together in hyperbolic geometry. I want to start with a lemma that's going to lead up. No. I'm going to start with a lemma that's going to lead us into a very interesting theorem. If the defect of triangle ABC is equal to the defect of triangle DEF and AB is congruent to DE, then triangle ABC is scissors congruent or equivalent by dissection to triangle DEF. Now, why does that matter? Because two regions that are scissors congruent, that are equivalent by dissection, have the same area. So what we're basically saying with this lemma is that if two triangles have the same defect and one corresponding side congruent, then those triangles have the same area. And the way this goes is actually very, very straightforward. We have triangle ABC and some other triangle DEF, but those are congruent. So what we do is we build the Sakari quads associated with each of those triangles. That is hideously bad. What do we know about the Sakari quadrilaterals as they pertain to the triangles? Well, what do we know about the defects? Well, the defect of this Sakari quad is the same as the defect of this triangle, and the defect of this Sakari quad is the same as the defect of this triangle. But oh my, these are Sakari quads with congruent summits and, wait, we don't know that. With congruent summits. And as soon as I have Sakari quads with congruent summits, then I know that the Sakari quadrilaterals are congruent. And once the Sakari quadrilaterals are congruent, then all is well. So it follows immediately that since the defect here is equal to the defect here, is equal to the defect here, is equal to the defect here, then triangle ABC is scissors congruent to triangle DEF. They are both congruent by dissection to the same Sakari quadrilateral. Okay, so that brings us to a place where we can handle Bholieyes Theorem. Bholieyes Theorem, well, that proof is just a tad bit more complicated than the one I just did, but it's no less true. If the defect of triangle ABC is equal to the defect of triangle DEF, then triangle ABC is scissors congruent to triangle DEF. The lemma gets us started. Bholieyes Theorem says, forget that one side may or may not be congruent. Doesn't matter if one side is congruent or not. If the defect of one triangle is equal to the defect of the other triangle, then I can cut the one up into triangular regions, cut the other one up into triangular regions, so that the little pieces are all in one-to-one correspondence with each other, and each of the little triangles on the one side is congruent to each of the triangles on the other. That's the basic idea there. Bholieyes Theorem is crazy, because in the hyperbolic, I mean, this is a result that does not hold in the Euclidean world. In the Euclidean world, the defect of every triangle is 0, and we know that you cannot cut up every triangle and make it into every other triangle. But in the hyperbolic world, because the defects vary, It is possible to say if the defects are congruent, if the defects are equal, then the triangles are scissors congruent. There is one other theorem that is just crazy. The area of triangle ABC is equal to some constant times the defect of triangle ABC for every triangle ABC. Every one. Area and defect play together in ridiculous ways. The area is just a constant multiple of defect. That is crazy. And it's based on this thought. Given two triangles ABC and DEF, the area of ABC compares to the defect of ABC in the same way that the area of DEF compares to the defect of DEF. So here's the thought. Let's focus on the defect, should be red. Let's focus on the defect of ABC as it compares to the defect of DEF. Let's pretend that that's 1. Let's just start easy. If that's 1, then we know from Bholieyes Theorem that triangle ABC is scissors congruent to triangle DEF, and we're done because that means the two triangles have the same area, and so you get this proportion holding nicely. So now we back up a step and we say, well, what if this particular ratio isn't 1, but it's some rational number, A over B? We'll pretend that A is less than B. It doesn't matter if A is less than B. We'll pretend. Well, what we do in this case is we take our triangle and we partition this side into B parts. This will be P0, this will be P sub B, and we partition it in such a way that if you connect all the dots, each of these little triangles has 1 over B of the defect of the whole triangle. So this defect is 1 over B, and this has defect 1 over B, and so on. It should be noted that if you were to find the 8th point along the way, this triangle would have A beefs of the defect. But we know that this triangle has the same defect as this triangle, so from the first part, they are scissors congruent. So if we were to take A of the B, we would have A beefs of the area. And so this turns out to be the ratio of the area of triangle ABC to the area of triangle DEF, and that's what we wanted. So the area of a triangle over its defect is equal to the area of any other triangle over its defect. Well, if the area to the defect is always the same, then the area divided by the defect is always the same. You've got a constant of proportionality going on there. There are some crazy results to this, crazy corollaries. There is an upper bound on the area of a triangle. because the area can only be 180 times the defect. So, no, let's try that again. No, not true. Whatever k is, the defect can't be more than 180. So once you establish what k is, area can be no bigger than 180 times that. I mean, you're used to thinking Euclidean geometry, where we just make the triangles bigger and bigger and bigger, and they have larger and larger areas. But in hyperbolic geometry, that does not hold. There is a maximum area for a triangle. Well, at least there's an upper bound. There may not be a maximum. There is an upper bound on the areas of triangles. Also, if the area of triangle ABC equals the area of triangle DEF, then triangle ABC is scissors congruent to triangle DEF. So any two triangles with the same area can be triangulated in such a way that the one has a bunch of triangles and the other is made up of a bunch of triangles, and they are in one-to-one correspondence where all the little pieces are congruent. That's insane. That's absolutely insane. And once you do that, once you have this result, then if R1 and R2 are polygonal regions, and the area of R1 is equal to the area of R2, then R1 can be chopped up to be R2 because you just break them up into triangles, and those triangles must be scissors congruent. I mean, that's crazy. That's crazy. In fact, as Venema points out at the end of his section, there exist triangles with the same base and height in length, but different areas. So there is no formula like, okay, we'll just do 1/2 base times height, because you can have the same base and the same height lengthwise, but different areas in hyperbolic geometry. And that is the kind of thing, this is the kind of thing we're going to talk about when we gather in class next time, because this is just wild. So there, that's a quick summary of areas in hyperbolic geometry. I hope to do it some justice when we gather together next time.